From UIST, Biplab, please take it away.
Thank you, Joel. Okay. Mobile apps are an integral part of our lives today. They are used by billions of users every day to perform tasks ranging from taking notes to checking bank accounts. With millions of apps available in online marketplaces, good design can be a key differentiating factor for apps, playing an important role in their adoption and ultimately their success. Designing mobile apps, however, is a complex iterative process with multiple design stages. In the UX design stage, designers try to understand user needs and develop flows that allow users to accomplish specific tasks. In the UI design stage, the layouts for the different UI screens are developed. Then, visual design details for these screens and their elements are added. Finally, in the motion design stage, screen transitions and element animations are added. At various stages of this process, prototypes are built and design feedback is collected to help refine the designs. To help designers manage the complexity of design processes, data-driven design tools have been used in domains such as web design, fashion design, 3D modeling, and graphic design. These tools have been used for finding examples for design inspiration, identifying patterns and trends, generating new designs, and collecting design feedback. In this work, we take a step towards bringing such data-driven design tools to mobile app design. Building data-driven design tools for any domain requires a repository of designs from that domain. In this work, we demonstrate how we can build such a design repository by mining designs from existing mobile apps. Before I present our specific approach, I want to highlight 3 key requirements any mining approach used to build such a design repository should have. First, it should be able to scale to a large number of apps. In general, the larger the size of the design repository, the better the data-driven techniques can perform. Second, apps can have hundreds of different UI states with thousands of ways in which it can transition from one state to another. A mining technique should be able to explore this state space. Also, only some of the paths in this space are meaningful or interesting to humans. A mining technique should be able to capture these interesting paths. Third, a mining approach should be able to capture the different components of an app's design. This includes both static components, such as UI layouts and visual details, and dynamic components, such as user flows and motion details. We developed an approach called interaction mining that meets all 3 requirements. It involves using humans to explore an app while capturing design and interaction data in the background. This approach is manifest in Erica, an interaction mining system for Android apps. Erica obtains apps from the Google Play Store and runs them on an Android device. Instead of letting users interact with these apps on the device itself, Erica lets them use these through a web application that can be accessed from a browser. Erica has 2 nice properties in terms of scalability. First, it does not require any modification to an app's source code, making it possible to apply this approach out of the box to the large number of Android apps available on the Play Store today. Second, this web-based approach lets users use apps over the internet, opening up the possibility of large-scale data collection through crowdsourcing. Now let's look at what using apps through Erica feels like. The 4 devices here in the background are running different apps. They're connected to a server that runs, Just give me a second. Oh, there we go. So they're connected to a server that runs our web application. In the foreground, a user is using one of these apps on a mobile browser in full screen mode. Erica can also be used on a PC browser. Using humans to explore apps allows Erica to meet our second requirement, capturing the states and interaction sequences that are interesting to humans. While users are interacting with an app, Erica continuously captures 3 types of data in the background. First, it captures the visual representations of UI screens in the form of screenshots. Second, it captures the structural representations of UIs in the form of a view hierarchy, an Android-specific representation that contains details of the layout as well as element properties. Third, it captures details of user interactions, such as their type and location. Now let's look at how this data is captured by Erica. So here's Erica again, Apps are run on the host device on the left, and users interact with them using a browser on the client device on the right. In the middle, a server hosts our web application and also saves captured data to a data store. On the bottom here, we show the state of the data store at different points in time. When a user interacts with the browser, the interaction details are sent to the web application, which saves it to the data store. It then makes a request for the view hierarchy on the host device. Once the view hierarchy is received, the web application stores it and then forwards the user interaction to the host device. If the app responds to the user interaction, any updates to the screen are captured as multiple screenshots and sent to the browser. This allows the user to see the results of her interaction. Once the UI settles, the user interacts with the browser again, and the whole process repeats. So this is how Erica captures these three data streams that we collectively refer to as an interaction trace. The main challenge in developing the system was to complete all of these operations in a fraction of a second so as not to hamper the user experience. That was one of the reasons behind using the more compute-capable server rather than the Android device to save all this data. The other way we lowered the latency was by using fast methods to generate the screenshots and view hierarchies on the host device itself. For screenshots, we used a library called Minicap that continuously monitors the screen of the host device. It captures screenshots anytime the screen changes at over 15 frames per second. For fast view hierarchy generation, we used a custom Android build that dumps UI data in XML format. This contains properties of the UI elements, such as their class name, ID, locations on screen, and displayed text. Unlike current Android tools that take a couple of seconds to dump such information, our implementation only takes around 0.1 second. So both these techniques allow Erica to offer the smooth user experience that you saw in the video. The three data streams captured by Erica show their power when we start combining them. Combining the screenshots with the user interactions allows us to visualize what users did in the app. The blue dots here show where users tapped or scrolled on these UI screens. The view hierarchy data helps understand the different UI layouts. It lets us get the text displayed in different UI elements without any OCR. Combined with the screenshots, it lets us crop out individual elements. All of this makes it possible for us to index elements based on their text or shape. Having multiple screenshots during UI changes allows us to combine them to visualize motion details. Here, we show how this particular screen responded to the shown user interaction. And finally, since this data is mined during human usage, it often captures meaningful user flows, which are sequences of UI screens that help users accomplish specific tasks. This, for example, is a search flow in this particular app. So this is how mining these three streams of data allows us to capture the different components of an app's design that we set out to do. We invited 28 participants to use Erica in a lab setting to collect interaction traces. Participants were told to use apps as they thought appropriate without any time limit for each app. Here's a glimpse of the data we collected. Overall, we collected interaction traces for over 1,000 apps that together contain more than 18,000 unique UI screens, 52,000 user interactions, 500,000 interactive elements, and more than 6 million total elements. To demonstrate the utility of this data set, we developed an application, a search engine for finding examples of user flows. Searching for examples is an important part of the design process. It helps designers get an understanding of the space of possible solutions and is useful for design inspiration. In the mobile app design process, designers often want to look at examples of user flows. This has given rise to online repositories such as UX Archive or Patterns.com that show user flow examples as a sequence of screenshots. These repositories, however, have failed to scale in the last several years. UX Archive, for example, has only 123 apps. This is mainly because examples have to be added to these repositories manually. Curators have to find flow examples in apps, screenshot the relevant UIs, upload them to the repository, and label them. These repositories are also limited in terms of the data that they expose. For example, having just screenshots prevents them from indexing individual UI elements, and hence users cannot search based on element properties. These repositories also lack motion details, an important component of an app's design. To overcome these limitations, we developed an approach for automatically identifying user flows in interaction traces. To do that, we first isolate the elements that users interacted with in these traces and separate them into icons and text. We then cluster the icons based on their shape and the text elements based on the words they contain. Each row of icons here on the top and each word at the bottom represent one such cluster. When inspecting these clusters, we realize that many of them have elements that contain semantic meaning about different user flows. We see elements here that denote flows such as sharing, logging in, and searching. These clusters helped us identify different flows that were common in our data set. For each of these, we developed element-based classifiers to identify them in interaction traces, helping us find examples of flows. For instance, we identified adding flows by looking for places where users interacted with elements that were shaped like a plus sign or that contained the words create or add. Here, we show examples of 3 such adding flows found in our data set. Here are examples of onboarding flows. These were identified by looking for UIs with Android view pager elements and elements with the words tutorial, skip, or get started. View pager elements are generally seen as a series of dots on the screen. However, it's much easier to identify them using the class names contained in the view hierarchy data that we capture. We identified close to 3,000 flow examples for 23 different flow types in our data set. We exposed these flow examples through an online search engine that allows users to search by flow type. Here, a user is looking for examples of search flows. This returns results from several different apps. Clicking on one of these results shows the particular screen in the context of an interaction trace. Users can go back and forth in the trace to get a sense of how the search flow was implemented in this particular app. Users can hover on individual screens to see how they responded to the shown user interactions. Users can also perform free-form text queries and find examples outside of the listed flows. Here, the user searched for flight. 6 results are returned by finding instances where app users interacted with elements that contained the word flight, either in their displayed text, class name, or IDs. This leverages the fact that app developers often use semantically meaningful class names or IDs in their code. So to summarize, we presented interaction mining as a way to mine design data from mobile apps. We demonstrated how it can be used to mine a large number of apps. And we showed how to use the resultant design repository to build a search engine for finding examples of user flows. This is just one step towards the bigger goal of making app design process more data-driven. In the future, we see 2 important ways for extending this work. The first is scaling up the size of the design repository. One way to do that could be to integrate a web-based interaction mining system like Erica with a crowdsourcing platform such as Amazon Mechanical Turk. Another aspect of scaling is to capture more states in each app. Here, we show the coverage for 3 different apps as we collect more and more human interaction traces for them. The coverage is in terms of Android activities, which loosely correspond to different tasks or features in these apps. We observed that for a complex app such as Yelp that contains a large number of activities, a large fraction of the app states are never visited by humans. Augmenting human exploration with automated exploration could help in capturing such states. The other avenue for future work is to explore additional data-driven applications. Earlier, I showed these 4 broad ways in which data-driven tools have been used in the design process. These include finding examples for design inspiration, identifying patterns and trends, generating designs, and collecting design feedback. Our flow search application is an example of the first. Based on preliminary results, we believe that applications in these other areas can also be built using the kind of data that we mined. For instance, for the first time, we can analyze motion design patterns. Here, we show the animation curves for all the sliding drawer menus in our data set. The screenshots and view hierarchies that we capture can be used to reverse engineer UIs, producing Android code that can serve as a good starting point for implementing similar UIs. Our data set can also be used for finding usability bugs. For instance, here are 2 screens that did not support scrolling, where users tried to scroll. Looking forward, we envision a world where data-driven design tools scaffold the entire app design process, making it easier to design mobile apps. Thank you.
Thank you very much. We've got lots of time for questions. Oh, great. I hope I have time to ask one. But go ahead, Paul.
Hi, Paul Ascenti at Adobe Research. This is very nice. I was wondering about privacy. If because your gathering data is so transparent, did people forget they were doing it and end up giving you screen captures that they probably really would rather not have given you?
Right. So for this specific data set, we collected the data in a lab setting where we actually provided users with fake user data. So we provided them with specific email IDs or phone numbers or location or any of those things that an app might ask for. But I do believe you bring out an important point, which is like if we were to crowdsource this, making sure that no personally identifiable information is contained in these traces would be very important.
Hi.
Hi.
Can you hear me? Great. I'm Mira Doncheva, also Adobe Research. I guess we have a lot of Adobe questions today. Really nice work, really nice talk. One question that came to mind is, it seems like visualizing what the user is actually doing in these examples is really important. And I noticed that you have some visualization of scrolling, as you showed. Can you talk a little bit more about other things you tried or what you think some of the challenges are in actually presenting this interaction in this kind of design gallery approach?
So as I mentioned, like we have animated visualizations for all of these different screens that show how a particular screen or how a particular element animated in response to user interactions. And I think that would be a good way to show designers and give them a sense of how the app works, how the app kind of transitions from one state to another, and so on. Other than that, I haven't really explored other visualization methods. So for now, we kind of have the static thing where we show these blue dots and try to give an idea of what the interaction was, and then we show animations that show how the app responded to those interactions. But I'd be open to any suggestions that you have on what could be useful ways to visualize this.
Okay, thank you.
Hi, great talk. I was wondering if you looked at how some of these interactions transfer between devices, like from mobile or from phone to tablet, or even if there's like a desktop representation. Have you thought about that? Are you able to cover that?
So right now, we haven't looked at that. So most of our traces were for a specific form factor. But our system is built in a way that if we wanted to, we can swap out those Android devices. Like we used Nexus 6 devices. The system is built in a way that we can swap out those devices and replace them with any other Android devices, such as tablets, and collect similar data. But going to desktop, I'm not so sure. The exact implementation would work. But I do think that the representation that we capture with like screenshots and the structural representation and interactions, I think that's more general and should be able to capture interaction dynamics in many environments.
Hi. Another question is, are you evaluating or like qualifying the screens and the animations? I mean, if you have that as a database also for screens and animations for other designers to look at, is there a qualification or evaluation if those screens are really like, living up to some quality assurance?
Right. So right now, this was just to give people an idea of what's possible with this. So we haven't really done that step where you qualify which ones are good examples, because in the future, what we're hoping would happen is we would have multiple traces for each app where different people might have searched in different ways, and it would be an interesting it would be interesting to see how we can do that. I think one way to do that would be actually, like if we were really crowdsourcing this, to have different stages of the crowdsourcing pipeline that helps us filter examples and pick out the best ones. The other way this could be done is like if this were to become a platform and is actually out there, designers who design their apps can go and kind of show the best way to use their app. and kind of have a reference kind of trace for, oh, this is how I intended search to be done, right? So that could give examples, like that could produce good show you what the good examples are.
All right, let's have our next speaker come up, and maybe I can ask a question while she gets ready. So this is a very impressive data set, and you've obviously spent a lot of time looking at the data set. I'm curious if you have any insights for how we could do better engineering of user interfaces based on what you've seen. Like, as a simple example, are there really messy view hierarchies for a very common design pattern where we could better support that in our toolkits?
So in terms of looking at implementations, right? So one thing we did notice was Android really doesn't enforce many constraints. So a lot of developers are free to develop a particular pattern in many different ways. So that makes it really hard at times to kind of capture the commonality between a particular thing you might be looking for. Different people might have implemented it in different ways. So I think that was an implementation challenge that makes it hard to do this kind of data mining. For example, some apps might have all their UI screens organized in one single activity. Others might actually break it down and kind of have more manageable activities and so on. So I think this freedom that Android provides is misused at times. And I think that would be one thing that I would point out as an implementation aspect that can be improved.
Great. Thanks. Let's thank our speaker again.